While electric current has both magnitude and direction, it is classified as a scalar quantity, not a vector. This is because it does not obey the law of vector addition. Here's a breakdown with examples. What makes a quantity a vector? A vector quantity has three key properties. 1. Magnitude, the size or strength of the quantity. 2. Direction, the orientation of the quantity in space. 3. Obedience to the law of vector addition. When multiple vectors of the same type act at a point, their combined effect is determined by vector addition, e.g., using the parallelogram law or triangle law. This means that both the magnitudes and the directions of the individual vectors play a crucial role in determining the magnitude and direction of the resultant vector. Why current seems to have direction? We often represent current with an arrow indicating the direction of flow of positive charge, or opposite to the flow of electrons. This direction is important for understanding the behavior of circuits and electrical components. Why current doesn't follow the law of vector addition? The crucial reason current isn't a vector is that when multiple currents meet at a junction in a circuit, their combination follows the scalar law of charge conservation, also known as Kirchhoff's current law, KCL. This law states that the algebraic sum of currents entering a junction is equal to the algebraic sum of currents leaving the junction. In simpler terms, the total amount of charge flowing into a junction must equal the total amount of charge flowing out. Examples. Imagine a junction in a wire where three wires meet. Example 1. Simple addition. Suppose a current of 2 amperes A flows into the junction from one wire. Another current of 3A flows into the junction from a second wire. According to KCL, the total current flowing out of the junction through the third wire must be 2A plus 3A equals 5A. In this case, even if the two incoming wires are at a 90-degree angle to each other, the outgoing current is simply the sum of the magnitudes. Vector addition would dictate that the resultant magnitude would be square root 2 squared plus 3 to the power of 2 approximately equals 3.6A, and the direction would be somewhere in between the directions of the incoming currents. This is clearly not what happens with electric current. Example 2. Currents at an angle. Let's consider two wires carrying currents meeting at a junction at a certain angle, say 60 degrees. Wire 1 carries a current of 4A into the junction. Wire 2 carries a current of 3A into the junction at a 60-degree angle to wire 1. If current were a vector, the resultant current in the third wire leaving the junction would be calculated using the law of cosines for vector addition. Resultant magnitude equals square root 4 squared plus 3 to the power of 2 plus 243 asterisk cos 60 degrees. Resultant magnitude equals square root 16 plus 9 plus 24 asterisk 0.5. Resultant magnitude equals square root 16 plus 9 plus 12. Resultant magnitude equals square root 37, approximately equals 6.08A. The direction of the resultant current would also be determined by vector addition rules. However, in reality, according to Kirchhoff's current law, the current flowing out of the junction in the third wire would simply be the sum of the magnitudes. Resultant current equals 4A plus 3. A equals 7A. The direction of the third wire would depend on the circuit configuration, but the magnitude of the current in it would be determined by the scalar sum. Conclusion. While current has a defined magnitude and direction of flow, it does not combine according to the laws of vector addition. Instead, it follows the scalar law of charge conservation at junctions. Therefore, current is classified as a scalar quantity, even though we often use arrows to represent its direction in circuit diagrams. The direction is important for understanding the circuit's behavior, but the combination of currents at a junction is governed by a scalar law, not vector addition.